Hi, good morning, everyone. Welcome to our webinar. This is Adam Benzion speaking, and I'm one of the co-founders here at Hackster. And I'm really happy to see everybody from all across the US and probably a few of you overseas joining our webinar. This webinar is going to be led by Cypress Semiconductors, and some of you obviously know Cypress. Cypress is the leader in advanced embedded system solutions, and you can find their products everywhere from automotive, industrial, home automation and appliances, consumer electronics, medical products, and more. And let me tell you a little bit about today's webinar. Today's webinar is going to be run by Pushek Madan. Pushek is an applications engineer at Cypress. He's been in the company for 8 years, and all in a variety of technical positions, from technical product management to application engineering. And he's currently working on developing the next generation solutions, which include new kits, new software, really cool projects for you guys to explore, and lots of really cool collateral. So in today's webinar, we're going to learn a lot about the PSoC analog coprocessors from Cypress. As mentioned in our promotion, that this is all about really sensors and learning more about the sensors that surround our world and how you can actually harness them. So you're going to learn about how to use cost-effective, simple analog sensor-based systems that integrate external analog front ends, how to enable rapid prototyping and design iterations with hardware and software flexibility using the PSoCKreator IDE and its components, and also how to tap into the powerful processors from ARM Cortex M0 Plus core. And of course, the PSoC analog coprocessors with block diagrams, the Pioneer kit, and other things that you could do with this particular board. So without further ado, I'm going to hand it over to Pushek and the Cypress team to present to you guys and show you guys a hands-on demo using the webcam. If you have any questions, go ahead and actually post them into the questions dialog box on the GoToWebinar app, and I'll make sure that Pushek and the team gets them and will answer them as they go. So I'm going to mute myself, and do enjoy your webinar.
Thanks, Adam. Hello, guys. This is Pushek Madan, and I'm Pushek Madan from Cypress Semiconductor. Adam just told you about me, and today we are here to discuss about PSoC analog coprocessor. Adam did give an introduction on the PSoC, a brief introduction on PSoC analog coprocessor and how you can use it for a variety of applications. And I will take you through the presentation where I'm put together a device for a variety of applications and the tool chain associated with the PSoC analog coprocessor, in which you can create your design and you can program the target hardware. And we'll look at the target hardware as well. So without further delay, I'll start with the presentation. So in the agenda, so we will be touch basing upon some of the terms of arts. So just to make sure that the audience, that's you and me, we both are talking about the same terms. We both mean the same thing when I'm using a particular term. Then we'll be going over the PSoCKreator IDE demo, how you can use that particular IDE to design your projects, design your solution using the PSoC analog coprocessor device. Then we'll be looking into the architecture of the PSoC analog coprocessor. So it will give you a good understanding on how to create a solution using this device. And then we will jump into the PSoC analog coprocessor Pioneer kit demo. You will see like how exactly you can program this kit, and you can use a variety of sensors on this Pioneer kit. And then we will be wrapping up with some of the references and links, and then you can ask questions about the design which you are thinking in mind. All right, so I'll start with the terms of art. So when I mentioned about the analog front end, it is an analog circuitry which takes a signal from one of the sensor and conditions that signal by passing it through an op-amp, an analog multiplexer, or a comparator. So you can use one or a combination of these blocks in your analog front end to condition your signal which you are taking it from the sensor, and then pass the signal onto an analog filter which can take the whole spectrum of analog signal and pass only a particular component at the output. So say for example, a low pass analog filter which takes a whole range of analog signal at the input and passes the signal at the output only lower than a particular frequency. So say for example, if I configure a low analog filter for 4 kilohertz cut of frequency, so it's going to pass the analog signal at the output whose frequency is lower than 4 kilohertz. And we can have low pass filter, band pass filter, high pass filter, notch filter. So all those type of filters do fall under this category. Analog front-end can also feed the signal into an ADC, or I can feed the analog filter's output into an ADC, which then converts the analog signal into a digital signal, which can then be processed by the CPU. And then we have a DAC, which is a digital to analog converter, which takes the digital value, converts it into an analog signal. We typically use it when we want to reference our analog front end or the external sensors to bias to a particular voltage. So that's what we mean by DAC. And then we have a signal processing engine, which takes the digitized value, aggregates the data, pre-processes the data, does all sort of processing on top of it, and provides the data to the host processor. So basically the signal processing engine, it is taking the data from the analog front, taking the data which is preconditioned by analog front end, processed by the analog filter and ADC, and then performing some actions on the digital value. It can go and update the DAC to take a corresponding action based on the digital value it has received, or it can simply pass on the value to the host processor. And when in this presentation we talk about analog coprocessor, we are talking about a device which integrates all these functions, that is analog front end, filter, ADC, DAC, along with the signal processing engine into a single device and interfacing with the host processor over a simple communication protocol to provide the sensor's data. And those of you who are not aware of PSoC, so PSoC is a programmable system on chip which has an MCU core built in, along with programmable analog blocks, programmable digital blocks, and with the interconnect and routing and the captions block. So you consider this as a complete system placed on a single controller. So typically you get a controller where you have an MCU core with some digital functions. But when I'm talking about PSoC, it's an MCU core with a lot of programmable analog blocks like op-amp, comparator, integrated inside the device, then programmable digital blocks like switch serial communication blocks, timer, counter, PWM, and programmable interconnect, which provides you the flexibility to route any block to any block, and the capsens, which is the industry's leading capacitive sensing technology. So all those things put together in a device is termed as PSoC. And the device which we are using here is the PSoC analog coprocessor. PSoC analog coprocessor is an analog coprocessor which brings in the programmable analog blocks like the UAB and the CTB. So we'll look into these definitions. The programmable analog block is a configurable hardware block using which you can create your AFEs. The programmable analog blocks consist of continuous time blocks, universal analog blocks, ADCs, and DACs. Let's look into what is continuous time block. So a continuous time block is a programmable analog block using which you can implement any of the continuous time functionality, like a programmable gain amplifier, op-amps, comparator, where the signal is continuously changing and you are implementing a continuous time function on that and amplifying the signal. So that is what we mean by the continuous time block over here. And then we have the universal analog block. The universal analog block is a programmable analog block, is a type of programmable analog block, which is a switch capacitor block in its base. Using that, you can implement any of the custom analog functions. If you want to implement an ADC, you want to implement that, you want to implement filter, rectifier, mixer. So using this universal analog block, you can implement a lot of different functions. You will see this in a little more details in how exactly it implements different functions using a couple of examples in our presentation. And then the programmable digital block, which is, as I mentioned earlier, which implements some custom digital peripherals that includes timer, counter, PWMs, and serial communication block. So without further delay, I'll quickly jump into my first demo, that is the PieceofCreator overview. PieceofCreator is the IDE using which we implement a solution or a design for the piece of analog coprocessor. I will jump into the PieceofCreator tool. So the PieceofCreator tool is available on our Cypress website. I'll provide you the link later on, or you can just go on the Cypress website and search for PieceofCreator. This tool is the IDE for all the Cypress PSoC controllers. On this tool, we provide a variety of tutorials using which you can have a look how to get started with a particular device, training for PieceofCreator, introduction to PSoC, and then we have a variety of code examples which you can download, which you can install on your machine. Like you can install a kit installer on your machine when you download from our website. As a part of the kit installer, you get all these different code examples installed on your machine. So you can either open one of these code examples and just open it on your machine, or you can alternatively go and create a new project. So when I create a new project, it asks me whether you want to create a new project based on a particular kit or based on the target device. So if I select a piece of analog coprocessor device which we are using, the development kit for this device is CY8C kit 048. So it shows you in the list over here that it is CY8C kit 048. So either I can select this, or I can go into the target device and select I want to use the piece of analog coprocessor. So for our today's session, let's select piece of analog coprocessor, and I'll click next. Then it asks me either I want to create an empty schematic, or I want to choose based on the code example which we have in our library. You can go to code examples, click next, and it will give you a variety of code examples, or you can choose to go for empty schematic. Let's go ahead with the empty schematic for this session. Then it asks me where do I want to keep the project. Keep the default settings, and I'll go ahead. So once I do this, it automatically creates a tool. It creates a project. As you can see over here, on the left hand side, it creates a workspace where I have the main.c in which I can program. And on the right hand side, I have a component catalog. I can choose to close this. In this component catalog, you can see there are a variety of components like ADC, op-amps, analog multiplexer, and in the middle we have the schematic window. So this schematic window is more like your whiteboard where you draw your schematic, configure the way you want your chip to operate, and just generate design. So this tool will take your schematic, it will generate the design as per that schematic, and it will generate all the library files, which later you can go ahead and configure in your main.c file. So let's implement a very simple blinking LED. So over here we have analog components. For blinking LED, on my board I have an LED which I will blink using the PWM. So my PWM is a digital function, so I'll go into the digital. There is a functions, so I can just drag and drop a TCPWM, which is configured for the PWM mode. If I click on this TCPWM, right click, there are variety of options available. That is datasheet, code example, component web page. For me to learn about how to use this tool, I can open the PDF. How to use this component, I can open the PDF, learn about this particular component, on how exactly, when to use this TCPWM, what are the input-output connections, what each input means, and how to configure that. It also has APIs, gives you all the information on APIs, how to configure those APIs. So this is your one-place tool, one-place information where you can get all the information needed to configure a particular component. So now let's just double-click on this component. I can either double-click it or right-click and select Configure to configure it as a PWM. Now I can either configure it as unconfigure TCPWM, timer, counter, PWM, or a quadrature encoder. Let's just go with the PWM. In PWM, I can choose how exactly I want my PWM to operate. I want it to left align, right align, center align. So based on the way I select it, it automatically updates a waveform over here, and it lets me visualize it, how exactly my PWM will be working. So I can have a PWM with dead time insertion, a pseudo-random PWM. So for our session, let's just use PWM where we do not need a kill operation. And if you need any of these functions, you can either select it from here, or you can select it as PWM with dead time generation. So in this particular case, let's say we want to generate a 1 Hz signal with 50% duty cycle. I select the PWM as a divisor of 65,000. Now my tool is smart enough to detect that my compare value is higher than period. So my compare value should always be lower than period. So it gave me an error. So since I want to generate a 50% duty cycle, so let's keep the compare value as half. So now you can see the output signal over here is showing as 50%. With this, I have configured my PWM completely. I just click apply and OK. Now my PWM is configured. Now I need to feed in a clock signal for this. Either I can go ahead and search in my component catalog, or I can just type in over here that I need a clock. I got the clock over here. I can drag and drop over here. And I also need a digital pin. So because I want to drive this PWM signal at the output, so I say digital output pin. Now I've dragged and dropped these components on the PC on the schematic window. Now I need to wire them up. So on the left hand side, you can see this wire tool. I can either click over here or just press the hotkey W. It will select the wire tool. I can click here, click on the one end and on the next to connect this wire. And I can press W to get the wire tool, click on the line and click on the pin. So now my tool has been, so if you remember in the PWM component, we selected the divisor as 65,000. So for that means I need the clock at 65 kilohertz. I can just open the clock component and feed the clock as 65 kilohertz and apply. So now based on this, my tool will automatically configure the clock frequency at 65 kilohertz, feed it to the PWM, and my PWM will feed this output to the pin 1. Now I have just placed this pin, but I want to map this pin to a particular pin on the controller. So for that, we have this CYDWR file, which is called the design wide resources file. I can go in this file. It has a variety of tabs, that is pins, analog, clock. So whatever we configure, it gets configured in this block. Now I need to select the pin. On my development kit, I want to drive the blue LED, which is connected on port 16. So I select, when I click over here, it gives me all the options. So I just select P16. Now it has done the mapping. Now I can just simply go ahead and generate the application. When I hit on this generate application button, whatever components which I have placed in this design, it generates the application for that. Means it generates all the library files which I need to use, which are required for my device. I do not necessarily have to go and modify these files, but if I wish to, I can go ahead and change these files as well. But for our application and most of the applications, all I have to do is just go ahead and program my code in main.c. Main.c is a standard, a C language code. Since in this particular case, we are just using a PWM, so I can simply go PWM_1_start. That is, so you'll see that as and when I'm typing, my tool is smart enough to detect what are the available APIs. So I can select, oh, I need PWM_1_start. That's it. And that is the only amount of code which I have to write. Once done, I can build the project using this build designer 1 button. And once the project is built, I can program the device using this integrate program button. So now on my board, blue color LED is blinking. All right. And if you want to export your project, you can click on so at times you want to work on the IDE where you are comfortable, say for example Eclipse or Kyle. After configuring your project in this tool, in the schematic window, once you generate the application, you can go to the project and you can export to any other IDE as well. So you can export the project to Eclipse, IAR, New Vision, or any of the other IDE. And then you can just take the project, since you have done the hardware configuration, and work in your own project, in your own IDE environment. All right, so with that, I will go back to the presentation. Now I'll talk about the PieceOC analog coprocessor architecture. In the PieceOC analog coprocessor, so this is how the device looks like. The PieceOC analog coprocessor has programmable analog blocks, the signal processing engine, which we talked about earlier, and the I/O system. In the PieceOC programmable analog blocks, we have a 12-bit SAR ADC, 4 op-amps. The 4 op-amps can work as a continuous time block. It means you can implement it as a programmable gain amplifier, comparator with variable comparator threshold, with all the resistors, capacitors integrated inside the block. You do not have to use any external resistors to be able to implement a programmable gain amplifier. Taking a step back on the SAR ADC, the 12-bit SAR ADC is a 1 megasample SAR ADC. If you wish to implement a high-resolution SAR ADC, this SAR ADC supports oversampling, using which you can implement a 16-bit SAR ADC all inside the hardware without having to do oversampling in the firmware. Then we have got 2 low-power comparators, which can work in the low-power mode. Please note, all the op-amps mentioned over here can also work in the low-power mode, that is a deep sleep mode. So they consume lower current as well. And all the op-amps have a comparator function as well. So if you're not using op-amp for PGA functionality, you can use those op-amps for comparator as well. So you can have a maximum of 6 comparator options. Then we have a 10-bit single slope ADC, which is separate from the SAR ADC, which I just discussed earlier. All the IOs are analog compatible. So in this device, I have 38 IOs, and you can use all the 38 IOs for your analog functionality. Then we have a PRB, which is called the Programmable Reference Block. The Programmable Reference Block is used to generate the reference voltage, which you can provide to the blocks operating inside the analog coprocessor device, or you can even route it to any of the blocks outside the device. At a time, you can have 4 programmable reference voltages, and these reference voltages can be generated using the internal band gap voltage or based on the VDDA supply. So you can, and all these programmable reference voltage, based on the band gap, you can have 16 tappings. So my internal band gap voltage is 1.2 volts, and you can have 16 taps on that. So it means you can have reference voltage as low as 75 millivolts. And then you can also multiply your band gap voltage to a level of 4. So you can have your reference voltage from as low as 75 millivolts up to 4.8 volts, all referenced using the internal band gap, which does not vary as per the VDDA fluctuations. Then on the universal analog block side, here are a few examples which are already implemented, but if you want to implement more, you can program the UAB, but we will also see in one of the examples where we have UAB configured for mixer and rectifier. But so over here we showcase that using UAB you can implement a 14-bit delta sigma ADC, a 13-bit voltage DAC, and the analog filters. The analog filter is a 2-pole low pass, high pass, band pass, and notch filters. And then we have the CapSense engine, which is for capacitive sensing. It can be used for any of the user interface application, or you can use the CapSense block to measure the capacitance. So if you have your analog application, if you're thinking of a project in mind where you need to measure the capacitance value, you can use the CapSense engine to measure the capacitance of the off-board components. Then on the signal processing engine, we have a Cortex M0 Plus core, which works up to 48 megahertz. So it's an ARM core. We have DMA, using which you can take data from these analog blocks and feed it directly to the communication block, where you do not want your ARM Cortex to be worried about some of the transfer of the data. Then these are standard CPU resources. And all the IOs over here can be routed to any of the analog blocks using the programmable interconnect and routing block, which we have over here. All right, with this understanding, let's take a look at a couple of examples which you can do using PieceOC analog coprocessor. So the first example shown over here is for the inductive sensing. So it's one of the use cases. So consider if you want to design your project where you want to do some robotics, and in that you want to detect a metal object, or you want to do some automation. In that you would like to detect where is the metal object. So in such applications, we use inductive sensing, and the way my PieceOC analog coprocessor solution works is, it drives a PWM so on the PieceOC analog coprocessor Pioneer kit, we have a simple PCB trace which is implemented as a coil. We drive that coil using PWM, and there's a capacitor outside. So that coil has an inductance, and with the capacitor outside, it implements an LC tank circuit. We amplify that signal and pass it to the down mixer. The PWM frequency driven is in terms of 12 megahertz. So we need either a very high sampling ADC to be able to measure an AC signal, which is switching at 12 megahertz, or we can use the UAVs to first down convert that high frequency signal to a lower frequency, and then implement a full wave rectifier all within the device to convert that high frequency AC signal into a DC signal and measure that using ADC. So when a metal object comes in close proximity with this coil, my signal drops, and I can measure that signal using ADC, and I can detect that a metal is in close proximity and a metal object has come closer to it. So a couple of examples over here. Here is a proximity sensor which is used to detect the coefficients for object detection. And over here, you can detect whether the door is closed using the inductive proximity example. And then in the next example, we have for the gas detector. It is more of a smoke alarm example. So in your house, if you have an LED which detects, which transmits a signal, and based on the smoke concentration, the photodiode over here receives a different signal. Here the op-amp is configured as a transimpedance amplifier or a TIA, which takes the current, amplifies it, passes it through the filter if I want to implement some particular filtering, then pass it to the ADC to measure the concentration level. And I can also implement electrolytic gas sensor where one of the op-amp is generating the reference voltage for the electrolytic gas sensor. And the second op-amp is configured as a TIA, which is taking the current in, measuring the signal, and then passing it to the processor. Then I can, based on the gas concentration or based on the smoke level, I can trigger the alarm using PWM, or I can pass it to the host processor. So here the PieceoC analog coprocessor solution is implementing a complete gas detector module where it is sensing the smoke signal and also measuring the gas concentration. So we looked at different analog blocks, but for your design, you do not have to worry about going and configuring those blocks in hardware or in registers. You can very easily do that in PSoC because PSoC provides you components which you can just configure by dragging and dropping it into your system. Once you drag and drop those components and connect it in your system, the PSoC automatically does the routing between those blocks and to the IOs the way you want to connect it. And when you generate the configuration, it provides you APIs using which you can dynamically control those programmable analog blocks as well. Say, for example, if you want to change the reference voltage on the fly, you want to change the cutoff frequency of the filter, or you want to change the gain of the amplifier, you can simply write into those APIs and change all those settings on the fly without having to going back and reconfiguring the hardware. So the way it happens in PieceofCreator is you just drag and drop those components, configure those components in the graphical environment, and wire them up for your design. So with that, let's have a look at the Pioneer kit, which we have with this particular demo, which we have for this particular device. So for the PSoC device, we have the PSoC analog coprocessor Pioneer kit. This Pioneer kit is available on our website for $49. Unique thing about this Pioneer kit is this Pioneer kit can work both as an Arduino shield, or it has Arduino compatible headers, and we ship headers along with the kit. So if you want to plug another shield on top of it, you can just solder those headers and you can plug another shield on top of it. Or if you want to use this as a shield and put it on a host processor where it does all the sensor interfacing, you can do that. This kit comes with 5 onboard sensors, that is the voltage sensor, resistance sensor, current sensor, inductance, and capacitance. So with these 5 different fundamental electrical quantities, you cover the entire spectrum possible for the analog sensing. So any of the analog sensor, the output signal is going to change in voltage, resistance, current, inductance, and capacitance. So this kit demonstrates how you can interface with those five different type of sensors. That is a PIR motion sensor, thermistor, ambient light sensor, inductive proximity sensor, and the humidity sensor. This kit also has the PSoC 5LP, which is configured as an onboard programmer. You do not need an external programmer to program this device. Although if you want to, you can connect that external programmer as well. But this onboard programmer can be used to program this target device. It can be used with PieceofCreator, or it can be used with any third-party IDE via CMSys DApp. So it supports CMSys DApp, so you can use that to operate this kit to program any of the third-party, to program the piece of analog coprocessor using a third-party device. So with that, now let's look into our second demo, where we demo the piece of analog coprocessor Pioneer kit. So I have piece of analog coprocessor Pioneer kit in my machine. I will just go ahead and program this kit with the demo file. So I have the PSoC project, which I'll just open for you, and I will program the device. And then we have a GUI using which I can showcase different sensors connected to it. So due to some complications, this one is not working. But what we can do, what we'll do is we will post this project on the Hackster platform, where you can take this project and the GUI. You can just program this hex file into the target device, and you can view the different sensor data. So what happens is, once you program the device, you can see the status of different sensor. You can click on each and independent of the sensor, go to their corresponding tabs, and view their different voltage levels. It gives you the digital value, and it also tells you what is the voltage what is the signal which it measured and at what point. So this particular demo will be posted on the Hackster platform, and we'll share the link in the community, just that you can go ahead and demo it on your site. With webcam, unfortunately, due to technical problems, webcam not working, I won't be able to showcase this demo. Now, on the Wrapup side, here are some of the useful links which you can use to get acquainted with the device, to get the kits, and some of the application notes if you want to get started. We have some of the analog coprocessor videos on our website. Some of the useful links are www.cypress.com/PieceofAC. On this particular website, all the related information, data sheet, kit, IDE, application note, all the related information is available on this single page. Plus, there are also independent links if you want to go directly to those websites. So now, with this, we'll take questions. So if you have any questions, please feel free to ask. If you have any questions, you can also type into the chat window and we can answer those questions for you.
Hi, this is Adam. So what I'll do is let me read some of the questions we received.
Okay.
The first question is, what is the LabVIEW used for PSoC?
For PSoC, we use PSoCCreator IDE to program the target device. If you want to use LabVIEW, you can use LabVIEW to automate the test and to talk to the device. There are on the device we have the PSoC programmer, which provides. We have the Kickproc, which provides the APIs, which you can use in the LabVIEW environment to talk to the target device. But the IDE used to program the PSoC device is PSoCCreator IDE. Although if you want to use LabVIEW, you can use it to talk to the target device via the Kickproc, and the APIs for Kickproc are available on our website. We can post a couple of projects on the Hackster platform if need be on how to interface the target device using LabVIEW.
Great, thank you. The second question is, 1 second, let me actually go to it. Does PSoC supports power and clock gating for energy efficiency?
Let me see if I understood the question correctly. Does PSoC supports clock energy, power and clock gating for energy efficiency?
Right.
So with power gating, do you mean that, if you mean, can we disable the power for some of the blocks which are used inside? Then yes, all the blocks inside the PSoC analog coprocessor are independently powered. You can choose to start and stop at your will. And same is the case with clocks. Whatever the clocks which we are using in the system, you can put them in, you can start them and you can disable them. Plus, the PSoC analog coprocessor has a variety of low power modes, so you can operate in low power modes for energy efficient applications.
Great. There's another very specific question about somebody's actually using a Cypress product and he's using a PSoC 5LP. Can you tell us a little bit about the difference between a PSoC 5LP and this processor?
Right. So PSoC 5LP is a extremely high-end controller with Cortex M3 core and a different programmable analog blocks. The PSoC analog coprocessor over here is on the other side is based on Cortex M0 plus core with some new blocks in the programmable analog frontend. So in PSoC 5LP, we had the filtering in the digital domain, but in the PSoC analog coprocessor, we have some new hardware IPs using which you can implement analog filters, you can implement DACs, you can implement a lot of custom analog functions inside that analog block. So PSoC 5LP I would rate as a different and a high-end controller in the analog domain, but the PSoC analog coprocessor is a mid-end analog front-end applications-based controller.
Great. Next question. I think I could probably even answer it, but I'll let you answer it. Can you purchase individual sensors from the kit? Sorry about that. I'll repeat it again. Can you purchase any sensors from the kit separately?
So on the kit, we have 5 different sensors, and you can purchase all 5 of them or any one of them separately. But they come pre-soldered on the kit, and if you choose to use any external sensor, you can buy it separately, and you can plug it on top of the kit as a shield as well.
There's another question. If this kit is accessible in Russia, I'm not sure, but we will. Alexei, who asked the question, if you pitch a really nice idea to the system, we'll definitely consider your idea and might ship you a free one. But otherwise, to address the question, can you buy this kit in Russia?
Yes, all the Cypress kits can be bought anywhere in the world.
All right, let's move to the next question. So I think about another question about buying the parts, the component from the PSoC. So I guess, again, same answer. So yes, just reach out to, you can either reach out to us at Hackster or reach out to Cypress, and any component on any Cypress kits is available to purchase in volume.
And just to add, Adam, just to add a little bit on that, so on our kit webpage, we have installer which provides the complete bill of material for the kit. So you can take any of those components, and we provide the DigiKey part number. You can just go ahead and search on DigiKey, and you can buy those components from DigiKey.
Great. Are there any DMA examples? It looks like the DMA wizard in Creator does not apply to PSoC 4 series.
We do have DMA examples, but just not released with this kit. We can release DMA examples with this kit. To answer the second part of the question, the DMA wizard does not apply to this, or is applicable for PSoC 4. There are DMA wizard. So DMA wizard for PSoC 5 and PSoC 3 is different as compared to the PSoC 4. So we do have DMA wizard for the PSoC 4, but we will post an example using DMA for this analog coprocessor device.
Awesome. There was another quick question. If this webinar is recorded, yes, it's recorded and will be available on the contest page. Next question, how about connecting other external sensors to the coprocessor?
So give me a minute, I'll go back to the previous slide. So on this kit, we have these Arduino shields. All these analog IOs, all the analog IOs of this kit are brought out to these Arduino header. You can choose to solder the headers and connect any other analog sensor using that shield, or you can connect directly to these headers. If you do not want to operate as a shield, you can directly connect it to these headers. So the short answer is yes, you can connect other analog sensors, and these are some of the ways using which you can connect those sensors to the board.
Awesome. Can the PSoC be used for industrial purposes? What would be the main feature to use it rather than other controllers?
Let me clarify the question. Can PSoCCreator be used for industrial application, or can PSoC analog coprocessor be used for industrial applications?
Yeah, let me try this again. Is a PSoCCreator can be used for industrial purpose? So I guess the answer is yes, right? And the other question, second part of the question, what would be its main feature to use rather than other controllers? Not sure. Maybe Sridhar, maybe you want to rephrase the question and repost it, and I'll ask it again Let me move to the next question. What is the bandwidth for this system?
So the complete piece of analog coprocessor runs at the CPU with 48 megahertz, and the core runs at 48 megahertz, and different analog blocks runs at different frequencies. So, for example, the ADC runs with a maximum sampling frequency of 1 megasamples per second, and my universal analog block and 8 runs up to 1 megahertz. Continuous time blocks runs up to 8 megahertz. So each and every analog block has their own independent bandwidth. All this information is available in our device data sheet. You can look into the device data sheet for the exact number of each and every hardware, analog and digital blocks.
All right, great. Next question. I think also the answer is Creator working only on Windows?
Yes, it only works on Windows. But if you want to work on any other environment, the way I showed that you can export your project into any other IDE, you can export it to IDE Eclipse, and you can choose to work on Linux environment. But if you're using Mac OS, then in the panels, you can use PieceofCreator as well.
Great. What's the minimum operating voltage supported?
1.7 volts.
Thank you. What is the core mark for this product? Actually, hold on. The question is for a different product, for the 483. So I'm not sure you can even answer that. It's for the CY8C4A5LQI 483. So I guess it's it's for the analog coprocessor. Sorry.
Yeah, this is for analog coprocessor. I do not have the number on the core mark for this particular product, but we can look into this and we can get back to you.
Okay, great. Can we turn off some of the sensors to conserve energy during operation?
Yes.
Great. I think you answered that. Can you interface with IDEs like Arduino? You said yes. Let me see. Can PSoC be used for high current environments for industrial applications?
The maximum voltage which PSoC IOs are tolerant to are 5.5 volts. At high current, you have to design your system in such a way that the voltage which is the current or the voltage which is entering inside the IO is not exceeding the electrical specifications of the device. So you can look for the electrical specifications in the device data sheet. But if you're taking care of those, then yes, you can operate it in high current, high voltage environment as well.
Okay. Is CapSense similar to what you have on PSoC 4? It's about the same?
Yes. So this device has the latest CapSense hardware, which we recently released with our other PSoC 4000S and PSoC 4100S family. It is the latest CapSense hardware which supports both self and mutual capacitive sensing.
Okay, great. Do you support like a PDM mic?
Not on this particular kit. We do not have the hardware to support the PDM PCM mic on this kit. However, if you choose to operate it as a shield, then you can have the PDM PCM mic supported on the other hardware.
We're almost done. A few last questions. What are the other options for programming or flashing the analog coprocessor except for the PSoC 5LP?
So you can use any third party or any of the industry available programmers. You can use it via any of the standard CMC staff-based programming devices, or the current kit also enumerates as a CMC staff programmer and a mass storage device, where you can just drag and drop a hex file in the device and it will program by itself. But again, CMC staff and masterage is done by PSoC 5LP, where you use the PSoC programmer to talk to PSoC 5LP to program the PSoC analog coprocessor. You can use that, or you can use Miniprop 3, which is available on our website. Other option is any of our prototyping kits, which are $10 to $15 prototyping kits. You can buy those kits, and it has a programming pins. You can use that to program the target device, or you can buy a J-Link or a U-Link based tool, and you can use that to program this analog coprocessor device.
Awesome. And the last question is, does the PieceofCreator have a power profiling feature?
No, it does not have the power profiling feature at the moment. But let me take a step back. If you mean the power profiling feature, you mean to measure the power of independent blocks, the real-time power? If yes, then no, it does not have the power profiling feature at the moment.
Yes, that's what Krish means. Yeah.
Got it.
So does not have it. Okay. Great. Well, I want to thank everybody for joining this webinar, and Pushek, thank you very much for presenting. This has been really, really good. This webinar has been recorded. We will post it as well as the deck to the contest page. So, and we're probably going to run other webinars around this product in the near future, so you guys can actually have more information and more opportunities to ask questions. And should you have any other questions, please reach out to us at Hackster, and we will help you out. So thank you, Pushek, very much, and everybody that joined the call, and we'll talk to you soon.
Thanks, Adam. Thanks, everyone.
Thanks. Bye-bye.